But I would like you to learn some alkene reactions. And the great thing is, on one level, they're all the same. So, but that's Monday. We'll get to that on Monday. Today we'll cover mostly structure and nomenclature of alkenes, and maybe get into this whole cis, trans, and EZ business. That would be kind of nice. And then we should finish that up. Oh, I was in the wrong week. Look at me. We should finish that up by Wednesday. You'll notice that I have some of chapter 4 on Friday. So the plan is we'll start chapter 4 a week from today. As it says in the syllabus, that material will not be on the exam. I always like to do that, and I know some students like it, some don't. It's the sort of thing I can't make everyone happy. But I like to leave a slop day right before an exam, instead of having the exam right after we end the material. I never know if something's going to go wrong, if there's some act of God, or if I get sick, or I'm not at the moment, but you just never know what's going to happen, especially in a semester like this. So that if we have to skip a day of class or something, we don't have to move the exam. That's why I do it that way. So you can always trust the syllabus in terms of what it says is going to be in the exam. I'm sorry, but I will not be having a review session. What I do instead of review sessions is I have lots and lots of office hours. So however, though, I've given you already a pretty extensive study guide on this exam and given you examples of some of the questions from last year's exam. So I think I've given you a lot of review material already. But we have tomorrow, we have Tuesday and Thursday office hours, and also the following Saturday. So if you have any questions on anything, please don't hesitate. That's what I'm here for. Your first OWL assignment should be due tonight. After I get home from this class, I will check my email, and certainly I will try to check it at least once more today after I get home. But I'm sure you can understand that I can't just sort of sit there waiting for people to email questions at the last minute. I'll try to answer all of the questions I can, at least by dinner time or something like that. I am well aware that there are some difficult questions in this OWL assignment. You will find that to be the case in all of them. It's often the case that I ask you kind of to go beyond, and I do that for several reasons. First of all, remember, you don't have to get every single point, right? You only need to average 70% to get full credit for OWL at the end of the term. But it's been my experience in the past that asking students to do some, maybe not every question like that, but a few pretty hard ones, even if those questions are not on something you need to know for the exam, let's say, but perhaps by working on questions like that, they will help you figure out something better that you do need to know for the exam. That's at least been my experience. That's what students have told me. Will exam questions be in the same level of difficulty as our OWL homework? Well, I've put sample exam questions on eCampus. And also your exam questions are going to be multiple choice. Those are not multiple choice. So there may very well be some questions on OWL that are harder than some of your exam questions. Some of your exam questions will still be pretty hard. Some will probably be pretty easy. And no, I'm not going to put out a list of what things are in OWL questions that you will need to know and what things that you don't need to know. I mean, I want to be helpful, but at the same time, I also want to treat you like the adults that you are. And my department expects me to keep a certain level of, keep this class at a certain level, even though it's a survey one semester class. This is a university, so my department expects that of me. But like I said, I don't mind having OWL have a few questions that are really challenging, because it's like I said, my students have told me that's when they figure out other things, so it's okay. Do the best you can. You don't need to get every last single point. Do the best you can. And tomorrow I'm having office hours, noon to 2 on Saturdays, and if I have to go to an additional session on Sundays, it's not like I'm not going to be around. So I can do that if need be. But if you have any questions from OWL that you want to bring to office hours tomorrow, please don't hesitate. That's what I'm here for. So let's see. I do have some reef questions for you today, and I want to just kind of close the loop on cyclohexanes. Maybe I'll finish up on cyclohexanes first, and then we'll do our reef session, and then we'll move on to the next chapter. Good. So it reminds me another question. Some of you have asked me about watching my Chem 227 videos, and there has been a lot of overlap so far. If you're curious, up until now, you probably could, but not today's, nor Mondays, because we're doing cyclohexanes there today and Monday, and maybe even a little bit on Wednesday. And we're going way beyond in 227 what I intend for you guys to get down in this class. So, you know, I don't know that I'm about to say every single last thing that you need to know about cyclohexanes, but if I had to, you know, at least think of some of them, certainly I would like you guys to be aware that cyclohexane is not planar, that although you can certainly draw methyl cyclohexane like this, it is not flat, that the most stable conformation of the molecule is chair-shaped, that there are two different chair conformations that are in equilibrium with one another. It'd be really great if you understood that there were axial and equatorial positions that, as you saw last time, interconverted when you do the ring flip conformation. That'd be really great. But, you know, becoming huge experts at drawing these things, I mean, and we're doing dye substituted things and what's the energy difference. We're just, and I think that's appropriate for 227. I don't think that would be right to bring you guys through all that. But I think it's going to be helpful for you to know about the structure of cyclohexane. Some of you have already brought up to me, and I think some of you are asking about owl questions on things like glucose or other simple monosaccharides. The reason that's relevant is glucose is a structure really similar to cyclohexane, except you replace one of the CH2s with an oxygen. So, there's direct carrying over from that. So some of those may look like they're a little far afield. They're actually not. It's a little more relevant than you might think. Which reminds me, I think in fact, I know I put it in my class notes. There's a structure somewhere in your book of glucose. I'm fairly convinced it's wrong. I'm fairly convinced they've given you the unnatural isotope or isomer of glucose. That's L-glucose rather than D-glucose. Not that I expect you to memorize that structure, of course. I would never do that to you guys. But in case you're wondering, I'm pretty sure that structure's wrong. So, so much then for cyclohexanes. Certainly these things are more interesting, more conformationally mobile, even than cyclopentane. Another interesting thing about cyclohexane that I think is worth knowing is that this molecule has 0 strain, no angle strain. All of the bond angles are 109.5 degrees. And also, and you can really verify this if you get your hands on a model, all of the hydrogens are perfectly staggered. There are no eclipsed interactions. So that's really why cyclohexane is special. Last time we went over the 2 different chair conformations of just plain cyclohexane, C6H12. What happens if you add a substituent? Let's look at methyl cyclohexane. No, I could have made this any substituent I wanted. Well, for starters, I can put that methyl anywhere I want. I think I'll put it here. And I've numbered the carbons only so that we can distinguish them. Those aren't IUPAC type numbers. I just numbered them so that we can follow this through the ring flip conformational change. But I don't mean that I've necessarily put the methyl in carbon 2. I guess the methyl is by definition in carbon 1, isn't it? Although I also don't think you'd name that 1-methyl cyclohexane. I think the 1 is understood. I think you would just call it methyl cyclohexane. So here, let me put in all of the other hydrogens. And this would be one of the 2 conformations. And this one, the methyl group is axial. And I believe I ended class last time saying that other things being equal, it's better for a substituent to be in the equatorial position if possible. You know, in certain polysubstituted compounds, as I think you'll find out in OWL, sometimes there's one or two, there's a group that has to be axial. And so then you want it to be the smallest possible group. But if it's possible for the group to go into an equatorial position, that's going to be better. It's going to be lower energy. And the reason is because this axial methyl group up here, and more specifically, all of the electrons in all of the carbon-hydrogen bonds, those are going to be near in space to the electrons in this carbon-hydrogen bond, which is also axial, and this one, which is also axial. So they're all relatively close to one another in space. That's an example of steric strain, that you've got, basically it just means that you've got more electron-electron repulsion in bonds than you really need to have. And that will be relieved after we do the ring flip conformation and get the methyl group in the equatorial position. Like I said, it's a fairly complicated thing, though I think playing with the molecular models will help you. Basically, to do the ring flip, all we need to do is grab any two carbons that are opposite of one another, and the one that's lower will pull up, and the one that's higher will pull down. And in the process, it's like the entire molecule turns inside out. And all of the groups that had been equatorial become axial, all of the groups that had been axial become equatorial, and that's going to be the case here. So let's say that we grab carbon 1 over here and pull it up in this direction, and we grab carbon 4 directly across from it and pull it down in this direction. And so as a result, everything's going to seem to move in that direction. That's why I put carbon 1 up here. That's where carbon 1's going to wind up. And the others will also shift accordingly. So now my methyl group on carbon 2 is going to be, not IUPAC carbon 2, right? But my methyl group is going to move to this equatorial position. And all of the remaining 11 bonds rather will be to hydrogens. And like I said, there's some complicated mental gymnastics needed to follow this all the way around. But I think if you look at it the way I've given you here, that you're pulling one end up and pushing the other one down, and everything kind of turns inside out. And then if you get, can make a cyclohexane on molecular models, I think it's something you'll be able to follow. I guess I don't really care if you're, absolutely fantastic at drawing these things. It's a little bit difficult to get all the bond angles right. But I think at this level, it's still something we can understand, given the amount of structure drawing that we've covered. And you can see that now my methyl group has moved to an equatorial position, and this is going to be lower in energy or more stable because you've gotten rid of all of those electron-electron repulsion interactions that we have when the methyl group is axial. And again, this doesn't have to be a methyl group, it could be anything. But you would still wind up with the same type of analysis. So this is going to be higher energy. So I will remind you, this type of flat structure is not wrong. It depends what you're trying to communicate or what you're trying to do. But this is not a bad structure for methyl cyclohexane, unless you're trying to show the correct geometry that's going on. And so, since this structure on the right is lower in energy, that means that the equilibrium is going to favor that direction. And really, we can draw the equilibrium arrows something like that, showing that the equilibrium lies to the right. Or in Gen Chem, the way you would have put it is, as this equilibrium is written, K is greater than 1. And all that is still true. And you could figure all that out. I may just be stupid. I don't think you're stupid. What's the difference? Well, the difference is the methyl group has changed from being in an axial position and has moved to an equatorial position. I wouldn't say the position of the methyl group changed. It hasn't left the carbon that it was attached to. But when we bent this carbon up and pulled that one down, the molecule underwent a ring inversion. And as a result, while still remaining attached to the same carbon, this methyl group is now equatorial. And the way you know that it's equatorial is by looking at the hydrogen that's also bonded to the same carbon. I think you will all agree with me, that is definitely pointing straight down, most definitely axial. So that means that the methyl group is equatorial. So these two are in rapid mobile, axial position is higher in energy than equatorial position. Yes, exactly right. And the reason is what I gave over here. It's because when a group larger than hydrogen is axial, and it could also have been axial but pointing down instead of axial and pointing up, right? Remember, axial is straight up or straight down, and equatorial is sticking out from the periphery. But when anything other than hydrogen is axial, you get these unfavorable repulsive interactions between the electrons in all those CH bonds over here and in these bonds to hydrogen over here. And that's relieved when the group goes to the equatorial position. That means this conformation is favored over this one. So that's really one of our main points here. And that would be true regardless of what the methyl is. Change it to whatever other group you like. And yes, you'll find a list of the values of the energy increases for the different groups. Of course, I don't ask you to memorize all that, please. I would never want you just to memorize a bunch of numbers. But they are known, all of those numbers are known. And yes, we can take any one of those back into our delta G equals minus RT natural logarithm of the equilibrium constant, and we can go figure out the ratio of one to the other if we wanted to. I don't think there's a soul listening to me right now that wants to, and I'm not too interested in it myself, but we could. All that stuff is still there. Mainly, I'm concerned that you can recognize that in a situation like this I almost said isomer, this conformer is going to be higher in energy than this one. And that really, I think, is enough for cyclohexanes. So while I would normally say go ahead and watch my 227 lectures if you want to, don't watch this one, because we go well beyond this. But I think that's enough of a treatment for us. First question, which of the following compounds can undergo hydrogen bonding? Or if you need me to rephrase that, which of those undergoes the most hydrogen bonding? Which of those best exemplifies the definition we gave of molecules that undergo hydrogen bonding? I think that makes it clear. I think there's one clearly best answer. Good. So what did we say is a compound that fully exhibits hydrogen bonding? Well, it needs to have, well, besides HF, that's one molecule it does. It's basically anything with at least one OH bond or at least one NH bond. You need to have one of those two things. And then the molecule can not only donate, but also accept hydrogen bonds. So I think only one molecule here has that description, this alcohol over here. Now, E has a nitrogen, and C also is an oxygen, but there's no OH bond or NH bonds. And yes, it turns out, as you learned in OWL, these molecules can act as H-bond acceptors, but not H-bond donors. This is the only molecule here that can act in both ways. So I forgot to press stop, so probably everyone got it right now. But anyway, the best answer is B, and that's fine. Good. So, oh, and I'll be putting these up on eCampus, as always. Next question. Wait a minute. Did I get the right? Yes. Oh, okay. This is from last time. I think this is pretty straightforward. How many distinct conformations does ethane have? Okay. Well, we'll call it there. And again, hopefully we can agree there's two major conformations of ethane, staggered and eclipsed. That's it. Things get a little more interesting once you start getting up to butane, but we learned about ethane, so yeah, I think C is the best answer. Good. And we'll make sure you get those 8 points for attendance eventually later. Going on here, click to exit, good. And again, don't panic, because what you see on the REEF website at any given time will probably be wrong. What I plan to do with after every, oh, I don't know, maybe not every class day, but every 2 or 3 class days, is I plan to go into REEF and download what they've got and then make all the corrections. You know, make sure everyone gets credit for attendance. There's always a few people that I have an excused absence for one reason or another, so I take care of that. And when it all looks good to me, then I upload it to eCampus. So anything you see in terms of REEF grades on eCampus supersedes what you see on the REEF website. Now, if you see something up on eCampus that's wrong, please let me know. We need to fix that. But if something, I sort of expect things to look wrong on the REEF website. I've tried. I can't make their gradebook look the way I wanted to. I told my 227 classes that I almost am tempted to tell you guys not even to look at the Reef website. I just sort of feel stupid saying that, but I'm very tempted to say that. I'm this close to telling you that. Good, so that puts us in good stead to start off on chapter 3, which is on alkenes and alkynes. And we're going to learn about the structure of alkenes and alkynes, their properties, their chemical behavior, which turns out to be all very similar, by the way. And that's important because alkenes show up in all kinds of different natural compounds. I can think of all different steroid and sex hormone type molecules that have cholesterol has a double bond in there, among other things. Alkene functional groups also show up in other molecules that are related to metabolism, for example. So if you learn something about how even smaller alkenes behave, then you get an idea of what that functional group does in larger molecules. Alkynes, I do have to be honest, there are not very many of them in biological systems. I can't say none. You do occasionally find a drug molecule or three that has an alkyne functional group. I'm thinking of one in particular, calicheamycin, which has been found to have anti-tumor and antibacterial activity, antiviral, and it's got, actually it's got an alkyne in kind of a stupidly large ring. As I recall, it's a 14-membered ring that contains an alkyne. I don't know where they come up with these structures sometimes, but it's rare. I can't say never, but there are not that many biologically active alkynes. Let's see. In the class notes, I took you through a fair bit of review from Gen Chem, some of which we've already reviewed, but since we still have, 20 minutes, I think we'll have time to re-review at least some of it. But I at least want to get us as far as naming alkenes, which, by the way, if you know how to name alkenes, that's at least 90%. Yeah, I'm comfortable saying that. At least 90% of what you need to know to name both alkenes and alkynes. The only added thing is to number where the double bond is, either in the chain or on the ring, or the triple bond for that matter. And the only other issue which I would like to at least introduce today, but we may need to leave the rest for Monday, is this whole issue of cis and trans. And then there's an added issue, which is, as you may very well have already noticed, it's not difficult to come up with an alkene whose structure breaks the cis-trans system. And so we need some way of naming the molecule in those cases. And that's welcome to the E and Z system. That's actually technically in chapter 5, but I'm moving it forward to here because I just think it makes more sense here. Good, so I think that's enough for an intro. In terms of naming these things, it's really not very different than naming, let me experiment. I wonder, you'd think that thing would give me straight lines. Oh, they are straight, but they're not necessarily exactly vertical and horizontal. Okay, thank you for letting me experiment. In other words, it's no better than this. So naming alkenes isn't all that different from naming alkanes. You first want to identify the longest possible carbon chain that contains the multiple bond or multiple bonds. And it makes most sense to start numbering nearer your multiple bond. So want to make sure about that. So I think you'll agree this 3-carbon chain is the longest we can get. You get the same thing going the other direction, by the way. No matter how you slice it, the double bond starts at carbon 1, and there's a methyl group in carbon 2. So I think the best name for this is probably 2-methyl propene. Hold shift. Oh, I was wondering. Okay, it probably does that with the straight line tool, but not with this tool. I'll have to maybe try that sometime. You would think holding shift would restrict it. Although actually I don't necessarily want them just horizontal or vertical, so we want some of them with 120-degree angles. Oh well, so I think 2-methylpropene is the best name for that. Prop because there's 3 carbons. 3-carbon alkane is propane, and the ene because there's a double bond. I've also seen this named like, and you'll notice I don't bother saying 1-propene. It's understood. Though I think you can do that as well, 2-methyl-1-propene. I'm okay with that. But it's understood. I've also seen 2-methyl-prop-1-ene. In Europe, they often do that. They might mention that on OWL. I'm fine with any of these systems. I think it's fine. I think anything like that is a good name for that molecule. Let's maybe do one more. Do a cyclic one, why not? What's the methyl for? The methyl is for this CH3 group, which is not included in the propene chain. Just a minute. Okay. So there are some rules, again, with cyclic compounds. You want to make sure that the sum of your numbers is as small as you can possibly get. I think it makes the most sense to start numbering so that your double bond goes between carbons 1 and 2. And then looks like we have an ethyl group in carbon 3. So I would call this one 3-ethyl. 3-ethyl cyclopentene, right? Yeah, the 1 is understood. 3-ethyl, there's no dash, just all one word. 3-ethyl cyclopentene. And the double bond is assumed. It's understood to be at carbon 1. Cyclopentene. So again, notice that ene ending for alkenes. And alkynes are named similarly, except you use -ine. And the nice thing about alkynes is you don't have to worry about cis and trans. It's linear. So a typical alkyne. So how many carbons do we have? 1, 2, 3, 4, 5. I'm just counting them so I don't screw it up. Looks like we have a 7-carbon alkyne, and the triple bond starts at carbon 2. So I think the best name for that guy is 2-heptyne. Hept for 7 carbons, and then YNE for the triple bond. And again, you sometimes see hept2-ine. I'm fine with that too. That's the European way of naming these things. I think they're both fine. But this is how we normally do it in the US. So, and I mean, I could go on with examples, but I think that will at least get you started with your practicing on OWL. But again, naming alkenes or even polyenes or alkynes or any of these things, it's just a spin-off of naming alkanes. Good. Let's see. Where are we at? It's 3:30 about. Okay, so I just sort of want to lay out for all of us what are the other things I want to talk about. I want to remind us of the relationship between hybridization and multiple bonds. We've gone over it already, and it in turn is a review from Gen Chem, but I think it bears repeating, which is, remember that a molecule, or rather an atom will adopt sp3 hybridization when it's fully saturated, when it's only got single bonds, when there's no multiple bonds. For carbon, that's when it will have 4 single bonds. That's when the carbon is sp3 hybridized, right? And it takes on tetrahedral geometry. Other atoms can be sp3 hybridized too, of course. The oxygen in water is sp3 hybridized. And it's as if the oxygen sits at the middle of a regular tetrahedron. The 2 hydrogens are at 2 corners of the regular tetrahedron, and the other 2 corners of the tetrahedron are where you find the lone pairs on oxygen. But it's still built on a tetrahedron. I think in Gen Chem you called that guy bent, which is correct. Or if your book was really fancy, it might have said angular. I don't care what you use. But it's still sp3 hybridized. And we could go on and say the same thing about the nitrogen atom in ammonia, right? All of those are sp3 hybridized. Why did I add the 2? Because that's where the triple bond starts. The triple bond is between carbons 2 and 3. So you put down where the multiple bond starts in these names. Good question, though. The reason I didn't do it in these is because it was at carbon 1 in both cases, the double bond. So it's assumed. I mean, I don't think people would tend to call this 3-ethyl-1-cyclopentene. It's understood that the double bond is at carbon 1. Here, the triple bond starts at carbon 2, so we have to say that, 2-heptine. Good, other questions? Oh, yes. I think you want the double bond to go between carbons 1 and 2. I mean, I don't think it's possible. Owl will be owl, but I've never seen one where you would do other than that. So I think that's the best way to go with cyclic ones. Good. Oh, yes, I'm sorry. Oh, hept2-ine. Yes, that's also acceptable. I was saying that's the European way of doing it. And I'm fine with both ways. In the US, we tend to do it more like this. To me, they're the same. So you might find those mentioned in OWL. I don't really care what you use. But people might think you're from Europe if you do it that way, which, you know, there are worse things than that. Yep, and I love it. People ask questions in chat and answer questions in chat. That's awesome. I love it, love it, love it. Okay, so anyway, but I want to continue going over this hybridization stuff. Then maybe we'll hit cis and trans, and if time permits, I'll introduce the E and Z thing, but maybe I'll leave E and Z for Monday. That's the thing that's the thing from chapter 5 that we're going to import in chapter 3. I get why they did it in chapter 5. I see why they did it, but I think it's going to be easier for us if we do it this way. Y equals triple bond. Well, ine, ene, and ane, yes, refers to alkynes, alkenes, and alkanes, respectively. Yep. So where was I? sp2 hybridization is what the atom will adopt if there's a double bond. There's one double bond coming off of the atom. And that's true for carbon, but not just for carbon. So the simplest possible alkene, I guess, would be ethylene. And yes, I guess the IUPAC name for this guy would be ethene, but no one calls it that. You can't have an alkane with fewer than 2 carbons. You need at least 2 carbons to make the double bond. And so we call that ethylene, E-T-H-Y-L-E-N-E. That's the trivial or common name for this molecule. And yes, if you wanted to call it ethene, E-T-H-E-N-E, it's not wrong. It's just no one really calls it that. But you find ethylene in crude petroleum, along with goodness knows what else. And ethylene is then used to make polyethylene, which I don't even know how many consumer products are made of polyethylene. So, but that's the smallest one. So both of those carbons are sp2 hybridized, have to be in order to accommodate the double bond. But it doesn't have to be carbons. We already talked a fair bit about formaldehyde. Formaldehyde is a molecule looking much like this. I didn't do a very good job at showing the correct molecular shape, but the carbon is sp2 hybridized, and the oxygen also is, because of the double bond. And sp hybridization is for triple bonds. So the 2 carbons in this alkyne will both be sp hybridized. They have to be. It's the only way to make that linear shape. And the only other time, I think I mentioned this, no, I'm sure I mentioned it. The only other time you ever run into something that's sp hybridized is if it has 2 cumulated double bonds. Cumulated meaning there's 2 double bonds coming off of the same atom, like the carbon in CO2. That carbon is sp hybridized, not sp2, but by necessity. It has no choice. It can't form those bonds unless it goes into sp hybridization. But that's pretty rare. Mostly sp hybridization is for triple bonds. So we went over all that already. There's some comments about bond strength. Of course, as the bond order goes up, the bond gets stronger. No big mystery there. And also as the bond order goes up, the bond gets shorter. Again, no big mystery. Certainly, I don't expect you to memorize any bond association energies, please. Please, I don't want you just memorizing numbers. Can't think of a worse use of your time. Well, there probably are worse uses of your time, but short of, you know, something malicious or hurtful to something, I can hardly think of a worse way to use your time. Good. That, I think, is all we need with that, and that gives us 7 whole minutes to cover cis and trans, and maybe at least introduce the idea of E and Z. So there's just one other issue with a good save. What did I, oh, yeah. Yeah, anyways, that's why they pay me the big bucks. Anyway, there's just one other structural issue with alkenes. And again, several of you have brought it up to me already, which is this issue of cis and trans. And I could bring it up if I wanted to use fairly simple molecules to introduce the idea. It would be to point out that there are 2 different butenes, and those are they. Or sorry, 2 different 2-butenes, because both of these have 4 carbons, and in both of them, the double bond starts at carbon 2. It's between carbons 2 and 3. But those compounds are different because you cannot rotate around a double bond in the same way you can rotate around a single bond. So these 2 compounds are permanently different. You know, you can't just turn one into the other by rotating around the bond. And so they need 2 different names. They are 2 different molecules with different properties. And by the way, welcome to stereoisomers. Right, so so stereoisomers are, I think we already said this, what, constitutional isomers have the same molecular formula, but the atoms are connected differently, right, different connectivity. And stereoisomers have same formula, same connectivity, but the atoms are arranged differently in space. And in this case, the atoms are arranged permanently differently in 3-dimensional space. You can't interconvert these 2. So therefore, they need different names. And we call this one trans 2-butene. Trans meaning that the 2 non-hydrogens, let's say, the 2 non-hydrogen groups are on opposite sides of the double bond. One's on one side, the other's on the other side. That's this guy, and this guy we call cis 2-butene, meaning that the two non-hydrogens are on the same side of the double bond. Here's an interesting question. This goes kind of beyond, but just for fun. If you had to make a wild guess, which of these 2 compounds is more stable, based even on what we've learned already about, eclipsed conformations and torsional strain and all that stuff, wild guess, which of those is more stable, trans or cis? Trans, and that would be absolutely right. Because in the cis isomer, those 2 methyl groups are kind of bumping into each other. And that problem is relieved in the trans isomer. So like I said, that's going a little beyond, but I don't mind asking you guys to make a wild guess. Good, so that's all fine. That means that if you had a molecule like, I don't know, how bad would this be? 1, 2, 3, 4, 5, 6. Looks to me like our double bond starts on carbon 3. We've got a methyl group in carbon 2. What about trans 2-methyl-3-hexene? How does that sound? Trans 2-methyl-3-hexene. I think that's right. You all seem convinced. I don't see anyone screaming and yelling. I don't want you just to believe me because I'm me. I do make mistakes. I screw up a lot, but I think I'm correct on that one. What about cycloalkenes? Well, I think you'll agree in cycloalkenes, the double bond has to be cis. It has no choice. It can't accommodate sticking in both directions. So no one calls that cis cyclohexane. It's just cyclohexane. It's assumed to be cis. The only other thing I can tell you about cis and trans is as soon as you see one of the alkene carbons having two of the same group on it, doesn't have to be hydrogens, two methyls, two ethyls, whatever, game over. There's no cis or trans distinction. So for instance, that guy. Well, this carbon has two methyl groups on it. So game over, there's no cis or trans. And we would call that one, let me see, 2-methyl-2-butene. So there is no cis or trans here. Why is that second one trans if it only has one alkyl group? Because the two non-hydrogens are on opposite sides of the double bond. So this alkyl group is on one side, this on the other. Tomorrow's office hours are noon to 2, more or less. 2-methyl-2-butene. So there is no cis or trans distinction with that. So as soon as you see two of the same group attached to any alkene carbon, game over. There's no cis-trans distinction. And I think that makes sense, because how are you going to say which is on which side of the double bond? It doesn't make sense. So those are the only caveats with cis and trans. But it doesn't take very long before you come up with a compound that breaks it. For instance, what about that guy? Well, we can't very well say if that's cis or trans, can we? We can say the chlorine is trans to the ethyl group. We can say the methyl group is cis to the ethyl group. That's fine. But what are we going to do with this molecule? And that we'll mainly leave until next time. That's where the E and Z system comes in. So I'll just introduce the ideas. We sort of do the same thing. We kind of look down the double bond. And what we're going to find is on each of the two carbons, I'll even write in the hydrogen so that we're clear on that. For each of the two carbons, we compare the two groups that are attached, and we play a little game of war. I don't know if people still play war, it's a card game. And we decide which one wins, and the one that wins is going to have the higher atomic number. So chlorine beats carbon. So chlorine's going to be the winner on this carbon. And over here, you've got carbon versus hydrogen. Well, clearly, carbon's going to beat hydrogen. So we find the two winning groups, winning meaning that you have the higher atomic number, are on opposite sides. And for opposite side, you use E. I'll go over this again on Monday. Opposite side, and for this, if they're on the same side of the double bond, you use Z, or Z if you swing that way, for same side. So if you're, along with me, one of the 11 people who took German in high school, you just won the internet. This is where that actually pays off, because these come from the German words. E is short for entgegen, which means on the opposite side. Z is short for zusammen, which means together. If you're not one of the 11 people that, like me, took German in high school, I have heard that there is a mnemonic device for this, which is same side. It's stupid as all get out, but it works. And most mnemonic devices work the best if they're kind of stupid. So we'll name compounds like that on Monday, but in the end, we'll want to call this, I think, Z, let me see, 2-chloro-2-pentene. Sorry, E2-chloro-2-pentene. That's what we'll wind up calling it. But we'll do more examples of this on Monday. So other than that, a little over time, sorry. So have a great weekend, and we will see you all on Monday.